In this video, we're going to look at how to characterize what we call rolling motion. So to this point, we've seen disks that are rotating about a fixed axis. We've talked about all sorts of rotational motion. We've talked about things like tangential velocities of different points on disks, tangential acceleration, centripetal, all this stuff. But if we're going to make this somehow applicable to the real world, where do we most often see things like disks that are rotating? And the answer is wheels, tires, right? And now, of course, nothing wrong with what we've said so far, but if we're looking for a real world example, it's hard to find something more apropos than the idea of a wheel. They're everywhere. So we've got to start to think about this from a couple of different perspectives. If this is the wheel of a car and you are riding in the car, right? Think about what is happening. You're traveling with some velocity. As this, of course, I've shown you the angular velocity of this wheel. As this thing is rotating, of course, the wheel is moving in this direction. So if you have a velocity that's in this direction, the wheel, of course, has to have a velocity in that same direction. But if you really, really think about it, that turns out to get kind of unclear. Imagine that you are riding along the axle here. So the wheel is moving and you're just kind of standing on the axle, and somehow you have worked it out to where you don't slip and you're just riding along with the wheel. What do you see? Well, you see this part of the wheel moving forward, but at a faster speed than you are, right? You've got some sort of tangential velocity up here that's moving forward faster than you're moving here. And you see this part of the wheel moving backwards, because when you look down, the wheel is rotating. But that perspective changes drastically if you're standing on the side of the road. You see the entirety of the wheel moving to the right. You see the axle here, the center of mass, moving to the right with some velocity. You see the top of this wheel moving to the right with a greater velocity. And when you look at the bottom of the wheel, when you look at this point here, you actually, if the tire is not slipping on the ground, you actually see this point sitting still with respect to the ground. So if you're looking at this thing as it rolls by, this turns out to be the center of rotation. And that's weird to think about, because when I say that this wheel has an angular velocity omega, our instinct is always to say, well, the center of rotation is right there at the center. And that's true from a certain point of view, a certain reference frame, if you want to use the physics word. If your reference frame is moving along with the wheel, then this is the center of rotation. But if you're standing on the side of the road, you see the wheel rotating about this point. Now, of course, as it rolls along, so does the center of rotation. It moves along with it, because this is what's called the instantaneous center of rotation. As this wheel rolls along, another part of the wheel comes into contact with the ground, and that becomes the center of rotation. So the center of rotation moves right along with the wheel. The main thing I want us to see from here is that if the axle, if you're looking at it from this perspective, from sitting on the ground, the axle has this velocity that looks like that. And if you think about it, this has to be the same velocity as the vehicle, right? The axle is what's not moving with respect to the vehicle. The wheel is turning around the axle, but the axle is attached to the frame if this is a car or if it's a bicycle, and it's just going right along with the rest of the vehicle. So how can we characterize this velocity in terms of the rotational motion? Well, the answer lies in really examining what we mean when we write down this equation, V tangential is equal to R omega. What we really mean, and it's tempting to look at this R and go, oh, that's a radius. Sorta, kinda, and very often it is, but what this actually means is that this is the distance from the point of observation, wherever we are summing up things about, to the point at which I'm evaluating the tangential velocity. That becomes more clear if I write this down in full calculus form. Where I have the cross product between the vector r and the angular velocity omega, where r is a vector that points from my point of reference, wherever I'm examining this thing, to the point at which I want to evaluate the tangential velocity. For this case, if the center of rotation is here and I pick there to evaluate this system about, r points from here, there. That's r. And as it turns out, this is the same as the radius of the circle. So what I get out of it is that this center of mass speed, the speed of the axle here, is some sort of tangential velocity, but using this as my center of rotation. And then this is the distance r, and then the omega of the disk is the same. So it turns out that the velocity of the center of mass in this case is still r omega. But I want you to see that the reasoning we got there is different. We're used to seeing this expression as saying, okay, here at the center, what's the tangential speed of a point here? We'll take that distance, multiply it by omega, and I get the tangential speed. I'm doing the exact same thing here, but the reasoning is slightly different. I'm now looking at this point where the wheel is in contact with the ground as my center of rotation. So the good news is I get an expression that looks exactly the same. So if you forget, it can still work out for you. But I do want you to see the reasoning here. We've got the center of rotation here, the center of mass here. So in effect, we're just shifting our perspective. Of course, I could shift it even more. What if I ask you, what is the tangential speed of the point at the top of the wheel from this perspective? Well, you can probably convince yourself that's going to look something like this. So the v of the top, well, what is that going to be? I still have an omega, but now the distance between this point and this the top of the wheel is not just r, it's now 2r, right? So I've got that distance is 2r. That's the important thing to remember. This r represents if we're not doing the full calculus treatment, this r just represents a distance. If we are doing the full calculus treatments, this r represents a displacement. But this r is going to represent a distance between my point of reference, wherever I'm putting my origin, and my point of observation, whatever point I care about. So if I care about this point, the distance is r. If I care about this point, the distance is 2r. If I care about the point in the middle there, the distance would be 3r over 2, wherever you want to decide to care about it.